Okay, folks, can you hear me? Can you see the image and can you hear me? Yes, no, just one person? All right, go back to default. Now, can you hear me? Good, thank you. Thank you. Make it this one high quality. All right, great. So everything is okay? Yeah, cool. All right, good afternoon, folks. And this is lecture 8. And we are on chapter 15. I just wanted to let you know that I changed the syllabus. I got an official email from the registrar's office about the final exam date and room number. So please go ahead and check the syllabus for the room number. It's a Willis 181. Check it there. And also the time is, I think it's a Monday, March 19th from 5 to 7 p.m. And if anyone has a conflict with that exam, that means they have another exam from 5 to 7, you gotta let me know in advance with the proof. And the larger class should give the uh, makeup exam. Suppose you have another class, say econ something, and that class has 350 students, which is much larger than my class, then it would be the responsibility of your econ instructor to give you makeup exam. And if my class, the size of my class is bigger than that, then it will be my responsibility. It's on the syllabus. It's on the syllabus. Please check it on the syllabus. And I sent you guys email a long time ago. You have it in your email. It's on the announcement, and also it's in the syllabus. I updated the syllabus. It's Monday, I think Monday, March 19 from 5 to 7. Lillis 181. I don't quite remember because I changed that on Saturday. So you need to check it yourself. Don't rely what I said. It's on Canvas. Click on syllabus and then you can see it. All right. Let's continue. And hopefully going through this chapter, you should be able to do your Excel assignment number 3. And here, last time we talked about, this is about sampling distribution. Things are getting more important now. I mean, not that previous stuff weren't important, but these are going to be, we're going to focus a lot on sampling distributions. And from here, we are going to move on towards confidence intervals and um, uh, uh, test of significance. And we do it for 1 sample, 2 samples, and that's it. That's the whole thing, the whole at the end of the lecture. So, and these are very important topics that we are going through. You got to understand them to be able to do well on second midterm exam. Anyhow, let's go through this. In chapter 15, I mentioned that we have 2 parameters and statistic. Parameters are used for basically population, and a statistic used for samples. And parameters for population, we say mean is shown by mu, and standard deviation is shown by sigma. On the other hand, for statistic, which is samples. So mean is usually shown by X and the bar over it. That's the mean. And standard deviation is usually shown by S. And this was an example. We went through this. And let's do another example here. It says, example 2, a group of middle school students measures the height of dandelions in a large field. Students are divided into 4 groups containing 5 students each, and each student measures the height in centimeters of one dandelion chosen at random. So these are randomly chosen. We assume that these heights are from a normal distribution with no unknown mean mu. Okay? Remember, when it says mu, that means you have the large field. We don't know what mu is. That's the population. So mu is the mean for that population, dandelions in the large field. But that's how we are going to use samples to extract that information about the mean of population. That's the whole idea. Okay, let's look at this one first. Here what we have. What is this sample mean X bar? That means this is sample 1, 2, 3, 4. So you got to find the mean of this. That's X bar, one sample. For the first group, that's the first group, the group's observation. What is the X bar? What is X bar for the first and 2 groups? Then we are going to find X bar for these 2 groups, and the third for the 3 groups, and the fourth for the 4 groups. So we want to show you that basically if the result, if the size of sample gets larger, so you have better values for your estimation or your parameter, whatever you're calculating. Okay, let's do this. So we are dealing with the group one. Group one, this is part group one. I'm going to call that one X bar. So we learned that if you want to calculate the mean of first group, you add all these numbers divided by the number of data points, right? 9.1 plus 16 plus 16.1, 1, 2, 3, 4, 5 divided by 5, and then you get the number is 14.04 centimeters. That is the X bar for group one. Now the next one says find for group 1 and 2. Now we want to look at that X bar. You can name this 1 here if you want it, 1 and 2 here. And then what we are going to add this time, so you're going to add the first row plus the second row divided by 10 because you're combining those. So we'll start from 13.7 plus 15.3 plus dot, 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 plus you come to the second row, you have 13.9 plus 9.5 plus dot, dot, all the way to the last one, that's going to be 13.5. And you divide number of data points, you have 10, you divide it by 10. And when you do this calculation, you have the number is 13.76 centimeters. So we do it for 3 of them. Group 1, 2, 3. And that would be X bar 1, 2, 3. So now we're going to add 3 of them. So the same thing, 13.7 plus 15.3 plus 13.9 plus 13.5. Now in the third group, you add 17.3 all the way to 16.2. But this time you have 15 data points divided by 15, and the answer is 14.4 centimeters. The last one is group is 1, 2, 3, 4. That would be X bar 1, 2, 3, 4. And again, you're going to add all the numbers from 13.7 to 16.1, then plus 16.9 all the way to 13.5 plus 17.3 all the way to 21.7 plus 13.2 all the way to, this should have been 21, divided by 1, 2, 3, 4. 4 times 5 is 20. And the answer is 14.74 centimeters. Okay, just change this one to 21.7, but that's 21.7 for 3 groups. Okay, we found these 4 means. This is a mean for each sample, for each group or each sample. We found that. And let's move on to the next definition. Now here, the definition is the law of large numbers. This is very important. States that the number of observations, if we increase that, the mean of the sample X bar approaches the true mean of the population mean. That is how we, based on this theorem that we have, that is how we find about the mean of the population. If you're dealing with a large number of data points, say you're dealing with, adult population of the United States of America. So if you're dealing with that, there are over 150 millions of them. You can't find the mean and go talk to 150 million people and ask about something and find the mean of that thing. So what do you need to do? So you pick some samples, and the samples, the size, the bigger the size of the sample, the better it's going to be. The number of samples, if you increase the number of samples, you get better results. If the sample size is bigger, you get better results. That means, and if you find the mean of those sample means, that represents mean of population. It's basically, it says here, the number of observation increases. That means you're taking data points. The mean of the sample, X bar, approaches the true mean of parameters, mu. If you want to do this, say this is like in a figure, you look at it. So this is the sample size. Let's call this one n. And suppose this is the mean, mu is the mean of the population. So suppose I have one sample here, right? Sample size is 1. So you might just get a number here. Then you have the mean, it's going to be one number. Now you have 2, a sample size of 2. The mean would be average of 2. It might be here or it might be there. It's very far from here. And 3, it's going to be here. 4, and if you increase the number of the observation for each sample, that means sample size increases, then you're going to get closer and closer numbers to basically the mean of the population. And you can see that this is in the direction that n is increasing. So we started with one sample size, one data point in it, then 2, 3, for each. At each sample, you find the mean of that sample, you plot it, and when you plot it, you can see that if you increase the sample size, you will get better result for the mean. It gets closer and closer to the population mean. That is the essence of this topic, basically. Now, let's do another example here. So we have example and example 3. Using the data set in example 2, calculate each group's sample mean. That means average of each group, each sample. Here, what we have, if you recall that this is not each group. This is first group, and then two groups, then three groups, and then four groups. So we are going to do for each group. So that means group one is going to be X1. We already calculated that. That is 14.04 centimeters. Remember, the size of the sample is n is equal to 5. The second group is going to be this bar, oops, X2 bar, and I'm not going to write it down. So all you got to do, add these 5 numbers, second row, add these numbers. Second group, add those 5 numbers divided by 5. Third group, add those 5 numbers divided by 5. Fourth, add those 5 numbers divided by 5. That would be the average of each sample. So I've done it, so I'm going to write it down. So this would be 13.3 centimeters, and n is 5. Group 3, that would be X3. That would be 15.86 centimeters. That's N5 again. You know, when you want to calculate the mean of sample means, you need to have fixed number of the data points in each sample should be fixed, like the way we have it here. So n should be 5 for all of them. You can't have n equal to 5 for one and n equal to 10 for another one. It has to be fixed for all of them. And group 4, X4, and that is 15.74 centimeters. That would be for n equal to 5. Okay, now if you want to plot this basically based on those numbers that's given to us, I'm going to do, this is going to be something, if you want to have this would be like a population mean is going to be here. That would be mu. And this would be okay. That would be the same as you have X bar here. That means if you have large sample sizes, the number of items in each sample is large. And if you plot on this pink curve, it's going to be the X bar is going to be closer to mu. In this case, I put it overlapped it. And you can see this is for the population. This is a hypothetical population. And this is for sample means. Okay? And the mean that you find here, that means each point here, this is, say, suppose this is, I don't know, X0 bar. That means you pick one sample, you found the mean of that sample, it's going to be this point. You found another one, that's another X bar 10. I don't know, you just plot them. So that means these are the each points that you pick here for the pink curve, those are means of each sample. Like if you put here, you have 4 samples here, you put 4 numbers here, starting from 13.3 and 14.04 and 15.74 and 15.86. We have 4 data points here for this one, for the pink one. But you need to have a lot that you can connect them together and you can get this answer. What you should notice here is also, when you look at the standard deviation for this is the standard deviation for population. Because you're dealing, this is a population curve. And the same thing, yeah, for standard deviation for this one, for this curve, you're going to see that it's going to be smaller. So this value would be um, x bar plus s. That would be for the sample. Okay. And what else? And this is, you're going to see that this S is going to be almost equal to sigma over square root of the size of the sample. In this case would be 5, square root of 5. Whatever the sigma is, that would give you the value of S. Or vice versa. If you have value of S, you get the sigma. Okay, now let's move on. What we have here, we did this. So this is a sampling distribution of a statistic. Here our statistic is X bar for every one, X bar 1, X bar 2, X bar 3, and so forth and so on, is the distribution observation when we take all possible samples of the fixed size from the population. So that means if you take all fixed size of the population samples, like yeah, say you have ideally, if you have a population of say 1,000 data points, and if you're doing taking samples of 20, and if you take every possible samples of 20, and if you plot them, you're going to see the mean of those sample means is going to exactly coincide with the mean of the observation points of 1,000 points. That happens. That is the essence of using sampling distribution to extrapolate information about the population. Okay, let's move on. So the sampling distribution X bar has mean mu and standard deviation of this. So you can see X bar, if you look at the pink curve here, if you look at the pink curve, so you have X bar, which is the same as mu, as is that one, and it has the value of the standard deviation for X bar for samples is S, but S is equal to, this is S. S is equal to sigma over square root of N, and N is the sample size. Sigma is the population, standard deviation of population. And S would be standard deviation of samples, sample mean. Okay. As long as the sample, basically, let's go back to here. The sampling distribution of X bar, that pink one, X bar has mean mu, we saw that. Standard deviation of sigma over square root of N. This one is going to be sigma square root of N. Let me just do it with this one again. This is S, the sigma over square root of N. That would be this S. Okay. And remember, this is the curve. Okay. As long as the samples are SRSs of size n obtained from population with mean, mu, and standard deviation of sigma. So the idea again, we are looking, what is S? S is the standard deviation of sample means. It's the pink one. That is S, standard deviation. And sigma is the standard deviation of the population. That is the ink. Standard deviation of sample and standard deviation of mu. All right. Uh, we have this. Furthermore, the sampling distribution X bar is exactly normal if the distribution of observations X is normal. That means if you have the distribution of observations, X points, like say you have 1,000, that's going to be your observation, 1,000 points. If you distribute that, if that is normal, definitely it says if you take sample of that population and plot the mean of these samples, that's going to be normal too. Excuse me. In the next definition, you're going to see that in any case, whatever you have, if you have large enough samples, number of samples is large, you're going to have basically the distribution, this pink one is going to be always normal. Distribution of X, a random observation, and the distribution of X bar is random sample mean. You got to differentiate between these. This is the pink one. This is the black curve. This is X. This is X bar, big X bar. This is observation for the population. Every point you see here on the black and the dark curve, every point is one observation point. The pink one, every point on the pink one is the average of each sample. Size of n. N could be 5, could be 10, whatever the size of n is. On this one, on the pink one, each point represents sample mean at that point. Like here, this could be 13.3 here. The next one could be 14 point something. So that is the mean for each point. But the black one, the one with the ink drawn, so that means each point is just a single point. You go back to these numbers. If you take the population, this is not the population, but the population is the field. If you take a large field here, measure all of them, that's going to be each point. Those are going to be observational points. These are going to be mean sample mean. Just want to make sure that you understand, you differentiate between here random sample mean and random observation points, data points. They're two different things. And from here, because in order to find new or other information about population, since it's large, we can't, talk or interview everyone. So we use this method to extrapolate information about the population. Okay, so basically now back to here are different, so they're different. They have the same center, that means mu is the same for both of them, but the distribution of X bar has much less variant than X. You saw that. This is, X is the population. The variation of the population is larger because you have larger standard deviation. It varies a lot versus the sample variation. It's smaller, it's narrower, it's closer to the mean. It doesn't vary that much. You can see it from the figures, from the curves. All right. I'm just gonna now plot it into, let me do it with maybe two colors. This is going to be similar to what I have here. Here, this is the mu. Here is mu plus sigma. That would be sigma. Then you have mu plus 2 sigmas, and so forth and so on. On this side, you have mu minus sigma and mu minus 2 sigmas and 3 sigmas there. So this is a population which deals with mu and sigma, which the observational point is x bar, x, capital X, and if we use sample, it's going to be something, it's going to be narrower. So therefore, you can see that mu is the same almost. Mu and x bar is the same, almost a. And now this is going to be something here, that's going to be S. So at this point, this would be, I'm going to write it like here, x bar plus S, or x bar is the same as mu, or I'm going to write x bar plus sigma over square root of n. As S is sigma plus x bar plus sigma over square root of n. And the same thing goes here. For the second one, it's going to be here, and that would be x bar plus 2s, and that would be x bar plus 2 sigma over square root of n. And the third one the same. On this side, this would be x bar, which is mu, the same as mu, minus sigma over square root of n. And the second one would be here, minus 2 sigma over square root of n. And the reason for that, because mu and sigma x bar is the same. And this is, we call this one x bar. And observation for this is going to be sampled. And then you want to show this, that's going to show mu is going to be the same. The sigma is going to be square root of sigma over square root of n, which is, this is the same as x bar, and this is the same as S. In Excel 3, this is what you're going to use. Every function that you use, there's the same. The only difference is when it says you have 1 observation versus 10 observations versus 50 observations. So your sigma is given. So first observation, 1 observation, square root of 1. The next B, part B, is it says 10 observations. That means square root of 10. And the last third one, it's going to be 50 observations. That means square root of 50. So, and the function is it's going to be the same, normal dot this, whatever you're calculating, everything is the same, except this part, the standard deviation. It's going to change. That's it. So now you can do your Excel, number 3. All right. Let me show you something. This is a good example from your textbook. Here, if you look at this part, this one, look at this figure here. This is the population that you're dealing with. Here is the population. From this population, with the SRS, you're going to take 10, you're going to take many samples. Out of those many samples, each sample size is going to be 10. You cannot change the size of sample. Make a decision at the beginning how many data points you're going to have in each sample. And if you do that, so then you take 10 points from the population. This is going to be sample 1. Find average of that. That's going to be this value. Sample 2, again, 10 people, 10 different people from the population. Average it out. That's going to be average for another 10. Sample 3, sample 4, 5, 6, 7, 20. And when you do that, now these points are going to be here on this line. So you can plot a histogram. From the histogram, you can draw some continuous curve too if you want it. But notice that when you get the mean due to the sample means here, that's going to be the same mean as the population mean. If you find the mean of all entire population here, each one of this is X, each one of these is capital X data point. But each one of these are X bar, capital X bar. Okay? The data points that you're dealing with. Anyhow, you plot them and this is what you get. And you ended up finding that the mean of sample means is the same as mean of the population. This is another example of, this is from, again, your textbook. Here it shows that if you have, these are different sample sizes. So it says, we plot this, if you look at here, based on the central limit theorem, large number, where I talked about it, and the distribution of a sample means X bar from a strongly non-normal, this is non-normal population, becomes more normal as the sample size increases. Here A, the distribution of one observation, sample size is 1. Here, the second one B, the sample size is 2. We can see that. Here on the C, the distribution X bar, sample size is 10. And the last one is the distribution of X bar, and the sample size is 25. So you can see that by increasing the sample size, you're going to get better answer. You're going to get more normal distribution, even though your population is not, it's non-normal. The sample distribution that you get, it becomes normal. Okay? All right. Let's do the next page. Next page is page 3. All right. So it says we take a sample of 4 observations with data from a normal distribution having mean 4.5 and standard deviation of 2. So basically, if I want to write this, this is n. My mu is mean is 4. I'm going to rewrite it like this. This is going to become n. Sigma is 4.5. Standard deviation is 2. This is a population. Now, it says, what distribution does the sample mean X bar follow? Okay. Remember, the size is, I got to put this n is equal to 4. It says 4, doesn't it? Somewhere said we take a sample of 4 observations. That means the size of sample is 4. So now we want to find for sample mean. So I'm going to rewrite this one. X is equal to X bar S. So that would be n. My X bar is the same as mu based on the, we said that, we talked about it. My sample size would be sigma over square root of n. And if you simplify this, this becomes n. And mu is 4.5. Sigma is 2. Sample size is 4. And if you simplify this, n is 4.5 and 1. Because the square root of 4 is 2. 2 divided by 2 is 1. Okay. Now, let's move on to the next one. What is the probability that an observed value from the population is greater than 6? Okay. It says from the population, so all I'm dealing My sigma is going to be 2. So basically, mu is 4.5. Sigma is 2. So I got to look at this one. So I'm looking at, it says, what is the probability of x greater than 6? I have to find this value. In order to find that, we're going to resort to what we learned before. Anytime it's greater than that, I got to look for probability for x less than 6. But remember, I got to convert this one to z-value, use z-score, and calculate the probability, right? So I'm going to write the z-score for that. Z-score would be x minus mu divided by sigma. X is 6, mu is 4.5, sigma is 2. And if you simplify this, you get 0.75. That is the z-value. So if you put it back here, you can rewrite this z greater than 0.75 is equal to 1 minus p of z less than 0.75. What is the question? For the square root of 4 is it plus? No, you don't put minus. No, you always calculate with the plus, yes. When you want to plot it, then you say, okay, I'm going to have plus and minus sigma. So we have this value. Now we got to calculate this. So what is it? We are going to go back and look at on table A. And we have here, we have to find 7.5. 0.75. 0.75 would be, this is 0.7. 0.75, that would be 0.75, and that would be, the value would be 0.7734. 0.7734. Okay? So this would be 1 minus 0.7, what was it, 7734. And if you subtract that, you get what, 66220, and the probability becomes what? For x greater than 6, the probability becomes either 0.2266 or 22.6. This is when you use the population, right? Now we are going to use what is the probability that the observed sample mean is greater than 6. Now we are looking at the sample mean greater than 6. So then we're going to use n. N is going to be based on what we calculated. Here, if you look at part A, your n is 4.5 and 1. So that means here what we have, here, what we have here is, again, mu is x bar equal to 1, and S is equal to sigma over the square root of 4, and that's equal to 1. Okay? Now we are calculating this time when x bar, because my data point now is x bar, the mean of each sample, it's greater than 6. That would be again 1 minus p of x bar less than 6. So I got to convert this one to z value. So my mean is, this is 6, still 6, right? Minus, and x minus mean is 4.5. And now sigma here is sigma square root of n, which is, we calculated, that's equal to 1. So that would be 1.5 divided by 1, and that's 1.5. So we got to find the z value. P of z greater than 1.5 is equal to 1 minus P of Z less than 1.5. So we are going to look at the uh, the uh, the table again. 1 minus Z is 1.5. Z is 1.5. That is 1.5, right? And 0, 0, that would be the first column because it's 1.5, and the number would be 0.932, 0.9332, 0.9332 minus 0.9332. So basically for P, when X bar is greater than 6, to subtract this, this is going to be 8, 6, 6, 0, 0, or 6.68%. Okay, you see that how we calculated this? This is going to be for Excel problems. You're going to do exactly the same thing. You're going to use normal dot-dist distribution. If it's greater than that, you're going to write 1 minus that. Instead of putting sigma value, you're going to write sigma over square root of n. That's it. You don't have to do separately. You can put it actually in the formula. Just replace, click on sigma, say divided by, then click on square root of n. You have n somewhere, square root of n in your Excel. Click on that, and that's it. And put the other values in the normal distribution function in Excel, then you get the answer. Okay, let's move on. Central limit theorem, we talked about this before. It's basically, it says a sampling distribution X bar is approximately, it's this one, mu sigma over square root of n. Regardless of the distribution of the population, it doesn't matter what the distribution of population is, it is approximately it's going to be this one. As long as we use a large enough SRS. Again, we talked about this too. Sample size should be larger, number of samples should be larger. And if you do that, basically, you see that X bar is going to be almost, this is approximately. This means approximately. So it's going to be normal. Another way of saying it, if you have even something like this, so this suppose you have something like this. This is the kind of skewed to the right. This is population. When you do with the samples, you pick the samples is going to be almost normal, almost. So forth and so on. You can see that it's going to be almost. And this would be for the sample. Again, the idea is you want to have large N. The number of samples should be more too. Get better answer. The mean is going to be the same for both. Okay. Now let's do example number 5. Example number 5 is, what is it? It says, let X be a randomly selected US person's net compensation as studied in example 1. Example 1, we had this, didn't we, somewhere? Example 1 This is example one. We have this value, so refer to that. Remember that income is usually very skewed, not normal for the population we're talking about, right? What is the mean of the distribution for X bar, a random sample of 8 US adults? So we said that if we have sample distribution, sample means, you have distribution of that, and if you find the mu of the mean of that is going to be the same as mu. So X bar is going to be the same as mu, and that's going to be $43,000, $43,039. So if you look at it here, net compensation, here what we have, that is the population, we call it parameter, and that is the mean. So this mean for sample distribution is going to be, remember in this case, my population, mu and sigma. We call this parameters, mu and sigma. Now, assume that we know the standard deviation of the distribution for X. Again, X is the population observation point, is sigma, which is this one. And what is the standard deviation of the distribution for X bar? So standard deviation for X bar, we said S is equal to sigma divided by square root of N. Sigma is $18,200. N is, what is N? N is 8. So S would be $18,200 divided by square root of 8 and square root of 8. And if you divide this, I got something, $1,434.67. This is correct. I mean, in a sense, it's correct because you can see that you have more variation when it comes to the population, which is bigger standard deviation, versus sample standard deviation, which is smaller than that. You have less variation because the sigma is smaller. Okay. All right. This is page 3. Now let's do page 4. Page 4, it's part C. We are working on part C. Let's see what part C is telling us, asking us to do. If we took another sample, random sample of 8 residents, what is the approximate probability that the observed sample mean is less than 60,000? So if I want to find that, what do I need to know? I need to know my X bar, it says, it's going to be less than one of the uh, um, um, observational sample means. This is a sample mean, one of the sample means. It's less than $60,000. So we want to find the probability of that. In order to find the probability of that, I need to know sigma. We have the sigma from the thing from the last page, and that's $18,200. Also, we want to know the size. The size is 8. So if you want to find X bar less than this, and the mu, what is the mu? Mu we calculated, it was 43,041 $2.39. That was the mu. So in order to find, this is your data point that you have here. You want to find what is the probability of this X bar to be less than 60,000. I don't have to write 1 minus because already X bar is less than that. So in order to find this, I need to convert X bar to Z. Z is equal to X bar. This is my data point. I'm going to write it X rather than X bar, then you don't get confused with mu. Minus mu divided by sigma. My sigma is square root of n now. Maybe I should put some kind of a S here when I write this differentiated from X bar. X bar would be mean of all the sample mean. All right, let's do this now. The Z is equal to X is, that is 60,000 minus mu is $43,041.39 divided by sigma is $18,200 divided by square root of n. N is 8. Okay, if you do this, your Z value would be equal to 2.63. So therefore, probability of Z less than 2.63 is the same as probability of X of S bar is less than $60,000. That is equal to, I gotta look at the table now. On the table, I'm looking at 2.63. Let's look at 2.63. This is 2.6 here, right? That is, that's 2.6. O3, if you go and look at it, O3 is fourth column. This is O3. That would be 2.63. So the fourth column here, 2.6, 1, 2, 3, 4. So that would be 0.9957, right? 0.9957. And this would be 0.9957 or 99.57%. So it says, so what is the probability of someone's salary is going to be observed? Sample mean is less than $60,000. It's going to be 99.57. That means almost 100% is under 60,000. The average, the mean the average population is 43,000. 60,000 is, it's going to be under 60,000. That's what we. All right, let's do the part D now. Part D is by how much must we increase the sample size in order to reduce the standard deviation of the sample mean by half? Okay. Sample mean is, the definition is sigma over square root of n. Okay. I want to change this one to 1/2 S. And my sigma is going to stay the same. And my n, this is going to be unknown. Yeah. So here, S is sigma over square root of n, because this is for the sample. We want to know, we are reading here. It's just, since I'm going to read it one more time. By how much must we increase the sample size n? That means n, in order to reduce the standard deviation of the sample mean by half. That means S is going to go from 1S to half S, 50%. So this is the general formula. Now I'm replacing S with half 0.5S, that's half. And sigma is going to stay the same. Now I've got to find what the value of N is. That's all I have to do. So the easiest way to solve this problem is don't plug the numbers at the beginning. Try to find what the value of N is, and at the end, plug the numbers. So in this case, if I want to do this, basically, easiest way to do this, I can, because I want to find N. I need to bring N up. So I can flip both sides. It's okay if you're dealing with math, you can flip both sides. This is S over 2. If I flip it, it's going to be 2 over S. And if I flip this, this is going to be square root of N over sigma. Okay? The next thing, I want to isolate this N. So in order to isolate this N, if I multiply both sides by sigma, this sigma is going to cancel with that sigma, and I'm left with square root of N is equal to 2 sigma over S. Now I got to find the value of N, not square root of N, so I got to square both sides. If I square this, square cancels the square root, so I have N equal to 2 sigma over S, the whole quantity squared. Now I plug the numbers there and see what the value is. 2 sigma is $18,200 divided by S. What is the value of S? What is the value of S? The value of S, what is it? We calculated. Originally, when you're dealing with 8, this would be sigma divided by square root of N, which is going to be this value. Yeah? You see it? So we put that value there. That value is, what is the value? I can calculate. 18,000. That was with the original size, 8. So if you do that, you come up with some number. The whole thing is going to be squared. If you put the values there, so you have just simplify this, then you come up with, let's see if I can do it in my head, 16. Four times, that's 32, almost 32, it's 32. So this becomes 31 plus 9, 6. So you don't have 31 plus 9, 6.96 number. It has to be whole number, so N has to be 32. So if you increase your sample size from 8 to 32, then your standard deviation is going to decrease by 50%. That's what it says. All right? Okay, if you don't have questions, let's move on and do the last part. Let the random variable f represent the number of fleas found on a given household dog. Note, this distribution is not normal, and it's not even a continuous distribution, since we can only have a whole number of fleas. Population mean from previous years is known to be 2.7 with the standard deviation of 1.8. So mu is 2.7, sigma is 1.8. Now let's do this problem, two problems. What is the approximate probability that a random sample of 9 dogs, n is 9, will have a mean of more than 3 fleas? So if I write this one n to be 2.7 and the sigma divided by square root of n, right? So let's write mu. This would be n, mu is 2.7, sigma is 1.8, square root of 9 is 3, and if you simplify this, n becomes 2.7, becomes 3, 1.8 divided by 3 is 0.6. That is what we have. Now, knowing this, we want to know what happens if you have, we want to find the probability of fleas, P of fleas greater than 3. That would be equal to, again, you go back to, this is instead of saying S here, little s. So instead of saying X bar, you're saying F bar because it's flea. You can put X and X bar S. So we're going to write 1 minus P F bar S should be less than 3. But I got to convert this one to Z. Use the Z value, Z score. Z score is X minus, in this case would be F sub S bar minus mu divided by sigma over square root of n. So F bar S is, what is it? It's 3. Mu is 2.7. Sigma over n is 0.6. So if you simplify this, this is 0.3 divided by 0.6, and that's going to give you 0.5. So this would be now, this would become P of Z greater than 0.5, it's equal to 1 minus P of Z less than 0.5. And this would be 1 minus, we can look at 0.5 now. 0.5 0.5 is, again, it's 0.500, so that would be this number, 0.6915. 0.6915. So therefore, this is the same as saying point Z greater than 0.5 is the same as saying that P of F bar S greater than 3. If you simplify this, you get 5, 8, 0, you get 0.3085, or the probability would be 30%, 30.85%. So based on the information we have, so this is going to be the probability of finding fleas, more than 3 fleas in a let's see. Can you please use a pencil so your mistakes don't mess up my notes? Pencils don't show really good, but why don't you use pencil? When I correct it, then you can correct yours. I'll use pencil, but pencil is not going to show well, good. Well, me here. Let's use pencil. See what the rest of you guys think if you want to use pencil. Okay, recalculate the probability of part A with a sample size of 1,000 now. Probability A, when we want to calculate A, we calculate the probability from part A. So this time n is 1,000. Then the rest is going to be the same, right? So that means, so if I want to write n is going to be 2.7 And sigma is 1.8 divided by square root of, instead of having 9, you're going to have 1,000. Okay, so if you simplify this, n is 2.7, and this would be equal to 0.057. Now we want to calculate the same probability with uh, with the same idea to see that what is the probability of having more than 3 fleas. So we are going to do exactly the same again, but the number is changing. The size of the sample is changed. Okay, so we got to find the z value again. Z value would be f bar s minus mu divided by sigma over square root of n. F bar is still 3, mu is still 2.7, and sigma is still 1.8 divided by square root of 1,000. Okay, and z is equal to, we calculate this, we come up with a number, it's going to be 0.3 divided by that is 5.27. So if you want to write this value, so for p, if sub s greater than 3, that would be 1 minus, we got to put the z here, the z value for 5, watch what happens. You don't have 5 here. The largest value is 3.499, you get 0.9998. So that means if you go down 5 point something, go all the way to the end, this is going to be even closer to the value of 1. So basically, it's going to be 0.999998, something like that. So another way of saying it, this is almost 1, almost. Therefore, that would be 0. If you use Excel, I used Excel to calculate this. Excel tells me that it is 1 minus 1 times 10 to the minus 8. What Excel did. So if I want to subtract this, 0.88 times that. So if you want to subtract it, you get something really, really, really small. They have 4, 4, 4, 4. That's the reason we say it's 0, almost. Okay. Now, let me ask a question. Do you guys want me to write with the pen or pencil? Oh, no pencil. Pen is perfect. Good, Peter. Good. Good. I'll write it from with pencil then. Okay. Uh, Either works too. That's good too. All right. Let's. Um, this is going to be chapter 16. Again, it's getting really, really important because the rest of the chapters deal. Basically, you have chapter 16, 17, 18, 21, 22, 23, all of them only deals with confidence intervals and and test of significance, basically. That's it. But for different cases, if you understand confidence interval, the the the, um, the concept, and also test of significance, if you understand what they are, then I guess it's going to be smooth sailing for you all the way to the end. But just I want to caution you that things are going to get more complicated because we are going to first we are going to talk about inference. Inference is confidence intervals and test of significance in general. So we are going to use this one for a single sample, which is going to be easy to deal with that. Then we are going to use it for when you have sigma of the population. When you don't have it, what do you do? So things are going to change, especially when we move towards two sample. Two sample, so when we use two samples for confidence interval and also test of significance, things get kind of messy, put it that way. But the procedure is the same. The concept is the same. So it gets a little bit when you introduce +4 method, it's going to become a little bit messy. Students usually get confused, and the best way to not to get confused is to pay attention, understand the concept, and do not let go of it. That, oh, I understood this in chapter 16 and 17. I'm okay. No, you're not okay. You got to continue, uh, focusing on the following topics, following chapters. All right. Let's get on with chapter 16. Chapter 16. Do we have time? 4 minutes. Let me just introduce you to chapter 16. In this chapter, basically, it's a statistical inference. That is what it is. When we talk about confidence intervals, and later on, we're going to talk about test of significance. So these are inference, statistical inference, and the methods that we use is basically we extrapolate information about the population by using sample data. That's what we are going to do. And the idea, the two things that we are going to deal with, one, it's going to be confidence intervals and tests of significance. Those are the important ones that we have to deal with. And in order to, minutes. Okay. So here, for confidence intervals and tests of significance, here basically, in this case, that what we are doing right now, in this case, we assume that mu is unknown and sigma is known. That's a condition for this one. We are doing it. Later on, you're going to see that we are going to go with the t-distribution. Something is not unknown, something is known. That's going to be different. So a confidence interval for a parameter gives an interval calculated from x minus d to plus x plus d. What does it mean? What it means, basically, this x stands for estimate of the population, basically. That x or this x is that one. So that means, again, this is towards again, we are extrapolating information about the population. What D means, D is basically, it's called margin of errors. So those x's are estimate of population, and that's margin of errors. We can rewrite this when we talk about confidence interval. We write it like this: we take x minus e, comma x plus e. So we need to know what d is. We need to know what x is. When we put it there, that's going to give you the interval that we call that confidence interval. So what it means, this confidence interval, what it means that the mu, for instance, here the mu, we are calculating about the mu. Mu is, if the confidence interval is 95%, that means 95% of the times, if you do the experiment, mu is going to fall between these two numbers. That's all it says. If you say with a confidence interval of 99%, that means if you take samples out of 100, 99% of that mean of the samples is going to lie between these two numbers. If your confidence interval is 80%, so that means out of 100, 80 times it's going to lie in between those two numbers. Okay, let's continue this on Wednesday. So you have the means to do your Excel number 3 now. And I have uploaded your Excel number 2 grades too. So I think the grades are up to date. All right, I'll talk to you folks on Wednesday. Thank you. Have a good afternoon. No, there is no Excel video because it's the same thing. The only difference is you're going to change sigma to the sigma over square root of n. Basically, you most likely you're not going to see any more Excel because you're using these functions. We're going to use these functions with minor changes. So you're going to see that again for confidence interval. So all you're going to do, you're going to calculate some of the things that you know already, you know how to calculate, but you're going to put them together in the form of confidence interval. The only thing it's going to be a little bit different, it's going to when we deal with the tests of significance. So again, those are again just kind of arithmetic calculations that means you know how to do it. So we'll get there. No, it won't be Excel video for this week. You're using exactly the same functions. The only difference is now your sigma has changed to sigma over square root of n. That's it. All right. Okay. I'm gonna stop. Have a good afternoon.